Electrons have a property called spin. Every physics textbook introduces it, and almost everyone then quietly says, do not take the word literally. An electron is not a tiny ball rotating on an axis. It has no known physical size, no surface to rotate. And if you calculate how fast its surface would have to move to produce its observed magnetic moment, you get a speed greater than the speed of light. Spin is a quantum number. It has no classical analog. It is one of those properties for which, in Feynman's words, there is no everyday experience to lean on. What spin actually describes is how an object transforms under rotations. If you rotate a classical object 360 degrees, it returns to its original state. An electron with spin 1/2 requires a 720-degree rotation, 2 full turns, to return to its original quantum state. This is not intuitive because nothing in everyday life behaves this way. But there is a demonstration. Take a belt, twist it 360 degrees, and it is tangled. Twist it 720 degrees, and with careful manipulation of the loop, you can untangle it without unwinding. This Dirac belt trick illustrates the mathematics of spin-half objects. Weakly. But it is the closest analogy we have. In 1922, Otto Stern and Walther Gerlach sent silver atoms through an inhomogeneous magnetic field, expecting a smear. Classical physics predicted a continuous distribution. Atoms with magnetic moments pointing in all directions should be deflected by varying amounts, producing a spread. Instead, the beam split into exactly 2 spots. Silver atoms were deflected either up or down, nothing in between. The magnetic moment, and therefore the spin, was quantized. Only 2 values, spin up, spin down. This was the first direct evidence of quantized angular momentum. Nobody had predicted 2 spots. Spin has an extraordinary consequence, the Pauli exclusion principle. No 2 identical fermions, particles with half-integer spin, can occupy the same quantum state simultaneously. Electrons are spin-half fermions. This is why electrons fill up atomic orbitals in shells. The first 2 fill the lowest energy level, 1 spin up, 1 spin down, and then the shell is full. The third electron must go to a higher energy level. This filling pattern is why atoms have the chemical properties they have. The entire periodic table, every element's behavior, every molecule, every material, follows from Pauli exclusion following from spin. Spin divides all particles in the universe into 2 fundamental categories. Particles with half-integer spin, 1/2, 3/2, 5/2, and so on. These are fermions, and they obey the Pauli exclusion principle. Electrons, protons, neutrons, quarks, all matter particles are fermions. Particles with integer spin, 0, 1, 2, these are bosons, and they have no such exclusion. In fact, bosons prefer to pile into the same state. Photons are spin 1 bosons. A laser works by encouraging enormous numbers of photons to occupy the same quantum state simultaneously. The spin of particles is not a detail. It determines whether matter exists as solid structure or as light. Spin was one of the last properties to be identified, not because it is subtle, but because nothing like it exists in classical physics. Dirac found it automatically in 1928 when he wrote a relativistic quantum equation for the electron. He was not looking for spin. Spin fell out of the equation. That is a remarkable moment in physics, the universe handing the theorist a property of matter that he did not know was there. Feynman said the most wonderful thing about physics is that the universe bothered to be so rich as to surprise us even when we are being careful.